Hello, everyone. My name is Doug Kreysar. I'm the CEO of Radiant Vision Systems, and thank you for joining this presentation. I'm excited to share with you a method that Radiant has created that significantly improves pixel level measurement and correction for very high resolution displays. We call this our fractional pixel method. We're all aware that the market is shifting towards emissive displays such as OLED and potentially in the future microLED, away from passive displays such as LCD with backlights. As a matter of fact, we've seen some very major display manufacturers announce production discontinuation of LCD panels, which can free up production for emissive displays such as OLED. And we're also hearing reports of other major display manufacturers focusing on microLEDs. These new technologies, emissive technologies, have advantages such as lower power consumption, but they also have some disadvantages in terms of the capability of producing these with high yields. One of the challenges of the emissive displays is that because they are individual emitters, each pixel is an individual emitter. The pixels from OLED and microLED displays can exhibit variability in luminance and color from pixel to pixel. This variability can be seen as non-uniformity across the display, and this can result in low yields of acceptable displays. What we show on the screen is an actual measurement from our Radiant software. This is a cross-section where you can see that from pixel to pixel, you can have variability of 10%. In this case, in order to increase yield and reduce variability from pixel to pixel, we want to measure each pixel and perform some type of correction to smooth out that variability. So in order to overcome the challenge of variability in emitters, we want to perform a correction. In addition to the challenge that I spoke about last time of creating a correction for each pixel, it's a little more complicated because each pixel on the display has its own response to gray level input. This means each pixel has its own gamma curve. So not only does our correction have to be for each pixel, it has to be for each pixel at each gray level. You can see that if we didn't do this, we may have uniformity at gray 255 in color, but then the color may change quite a bit for each individual pixel as we go to lower and lower gray levels. So we need to perform a correction at each pixel and for different gray values. Now that we've introduced the need for pixel level correction, or what we call DEMURA, let me give a few more details about pixel level correction. The process for pixel correction, or DEMURA, is comprised of 4 steps. The first step involves taking a high-resolution image-based measurement for each primary of the display, red, green, and blue, at various gray levels. For each of those measurements, you do a registration. The registration means that you apply a region of interest to each pixel in the display. The next step then is you take the average of each region of interest at different gray levels and save that as a measurement. So now you've got, based on the first 3 steps, a measurement of every pixel for the luminance, for the primaries, at different gray levels for each pixel. Finally, based on those measurements, you compute a correction factor that will allow the display to give a uniform pattern for all gray levels. This slide shows an example of an imaging system measurement of display pixels. On the left-hand side, you see a bright blue area that is a display pixel. This is many different smaller squares that are sensor pixels. In this example, you can see a circle representing the display pixel that has a diameter of approximately 10 sensor pixels. The region of interest is the green circle around the bright blue area. And of course, on the right side, you see that you have many pixels measured at one time. The key is that you want to be able to accurately place the region of interest around the bright blue area and not overlap others. And it's quite easy when you have approximately 10 sensor pixels across, as we do here, but it gets much trickier when you have very high resolution in your display versus the resolution of your imaging measurement device. In the previous slide, I showed a very nicely centered region of interest around lots of sensor pixels that comprise the measurement of a display pixel. But as we will see later in the presentation, when we have much less sensor pixels per display pixel, that gets much more difficult. And what happens if that results in an inaccurate measurement? The problem with an inaccurate measurement is that it will result in a bad correction. So as you can see from the example on the right-hand side, you have some bright pixels and some dark pixels, and this can be seen by the human eye. So if you take a display and correct it to something that looks non-uniform, you do not help your yield, and we failed to do what the pixel correction was meant to do. So 2 slides ago, I showed an image where the measurement pixels were about 10 across for one display pixel. But let's take a look at what's happening now in the marketplace. You can see that the latest cell phones that are being delivered have 3000 by 1500, 2500 by 1000 display resolution. And a high performance imaging measurement system may have 43 megapixels, 8000 by 5000 sensor resolution. If we do the math and take into account the aspect ratio of the display versus the aspect ratio of the sensor, etc., we can see that actually the sensor pixels per display pixels are not 10 across, but can be something like 2.5 across or 3.5 across. This can result in some very challenging measurement examples, and it requires some new technologies in order to ensure that the measurements are repeatable and accurate. So the new technology that Radiant has developed, we call the fractional pixel measurement method, and this allows us to get accurate and repeatable measurements even though we do not have a very large amount of imaging measurement sensor pixels compared to display pixels. The purpose of the fractional pixel method is to enable precise pixel registration and more accurate pixel level measurement over previous methods, regardless of imaging system resolution. The fractional pixel method is now widely used for DEMURA correction processes to dramatically increase OLED display production yield, and is also now being applied for new display technologies like microLED. The first challenge that the fractional pixel method addresses is registration of the pixel displays. As we've talked about, this is the first critical component of accurate pixel level measurement and correction. A dynamic registration technique was originally used by Radiant for the purposes of measuring individual LED pixels in large format outdoor screens, like this arena display. For dynamic registration to work, positioning the measurement region of interest, or ROI, around a pixel relies on a standard centroid position in order to be accurately and automatically placed. In this traditional measurement approach, the centroid position is the center of a single image sensor pixel. For LED screen applications, takt time was not an issue. Our original outdoor stadium screen corrections could take several nights. We took many measurements of a single display in order to focus only on small sections of the LED screen at one time, thereby increasing sensor pixel resolution versus display pixel resolution. The ROIs were aligned to the measurement system's image sensor array. We had many image sensor pixels across each LED display so that restricting the ROI to be centered on sensor pixels resulted in a region of interest that captured only the measurement data on the LED of interest and didn't include any information from neighboring LEDs. For cell phone production, we don't have several nights to correct one display. We have seconds. So we cannot measure the display in many sections. Instead, we must measure extremely high-resolution emissive displays in one measurement. We don't have the luxury of so many sensor pixels per display pixel. The image shown here gives a more accurate example of the scenario we now face, measuring new high-resolution displays. Here we have about 2 by 2 sensor pixels covering a single display pixel. The question is, where do we put the ROI? The region of interest, or ROI, should be positioned in such a way to cover the entire display pixel and exclude all of the neighboring display pixels. Ideally, the ROI should be positioned right in the middle of the center of the display pixel. But in traditional methods that we've described, the ROI is centered on an image sensor pixel. Given this constraint, we are now excluding significant areas of the display pixel and capturing a lot of areas outside of it. The fractional pixel approach solves this issue by not restricting the ROI to be centered on a single sensor pixel. Instead, this ROI can be anywhere in the image, and where it's located is determined by weighting the luminance of each pixel and setting it to the centroid anywhere in the image, thus matching the ROI with the exact center of the display pixel. In this method, we can provide more accurate registration even when pixels and subpixels are very closely spaced. This helps capture the exact display pixel area and prevents overlap from neighboring display pixels, minimizing crosstalk or contributions from other display pixels into that specific display pixel measurement. Just like we use the fractional pixel method to help us improve the accuracy of the registration, we also use the fractional pixel method to help us improve the measurement. As you can see in the image, we have a lot of pixels in a region of interest which may be partially inside the region of interest. And how do we use those pixels? Well, in the fractional pixel approach, we're able to use the pixels that are partially enclosed inside the ROI by using a portion of their contribution. In our 2 by 2 sensor pixel example, we need to make the most of the limited image sensor pixel areas within the ROI to determine precise luminance values. In the left image above, we show the traditional whole pixel approach. In terms of measurement, we're telling the measurement software that if the ROI encompasses more than 50% of a sensor pixel, then use 100% of the luminance of this pixel to contribute to the ROI. And if the ROI captures less than 50% of the pixel, then contribute 0 of that sensor pixel to the ROI value. The problem is that we risk losing significant data by ignoring the small partial sensor pixels, or capturing too much information by using 100% of the partial pixels. But using a fractional pixel approach, we can be much more precise in our measurement process. If you look at the image on the right, this is what we're trying to do with the fractional pixel approach. The signal of each sensor pixel is weighted by the area of the image sensor pixel within the ROI. This signal is then summed up to determine the overall luminance value of the ROI. In this instance, we get a very accurate determination of the luminance within this display pixel and have much less contributions of potential crosstalk with neighboring pixels. So I've shown the method of the fractional pixel approach and tried to explain why it should be better than traditional methods. In the next section, let's take a look at some experiments we ran in order to show the improvement of the fractional pixel method over the traditional methods. In our experiments, the very first thing we did was established a highly accurate pixel level measurement by using a microscope objective to capture a very high resolution image of some of the pixels of the display. Here we have our reference measurement on the left-hand side. This is what we're going to call the truth. This is sensor pixels approximately 30 by 30 for each display pixel. To simulate a more typical measurement, the image on the left side was downsampled to get the images on the right. The image on the right estimates a 3.2 by 3.2 sensor pixel per display pixel, which is much closer to what we see in the previous examples using current imaging measurement systems with current cell phone displays. Luminance values for each pixel was measured for the reference measurement, and this provided true luminance values. Luminance values from the downsampled measurements were created by using both the whole and fractional pixel methods. So the traditional methods and the fractional pixel methods. And we're going to compare the luminance values of those versus the reference. In this slide, we show synthetic measurement images produced by each type of measurement we just talked about, the reference, the traditional whole method, and the fractional method. A synthetic measurement is simply a measurement where one measurement pixel is one display pixel. In these measurements, you can see that the reference is smooth and appears much more like the fractional method versus the whole pixel method, which is much more variable, much less smooth than the reference measurement. Let's look in more detail. Here is a close-up of a synthetic measurement from the reference on the left and the whole pixel method on the right. Here's a close-up of the reference measurement, the high-resolution reference measurement, and the much lower resolution measurement done by the fractional pixel method. And we see the agreement is much higher. Let's take a look at a cross-section of the data where it's easier to show numerical values to compare the data. This graph shows normalized luminance for a row of pixels as measured by whole and fractional methods for the downsampled image, as well as luminance values for the row, same row, for the high-resolution reference measurement. We can see measurements of the fractional pixel method, the solid orange line, and the reference method, the solid gray line, closely match each other across the row of pixels. On the other hand, the measurements captured by the whole pixel method, the dotted blue line, exhibit a noticeable deviation from the reference values. The same data shown a different way is showing the percentage error in luminance as measured by the whole and fractional pixel method versus the reference. And here we can see the error of the traditional method is plus and minus 10%. However, the error of the fractional pixel method is more along the lines of plus and minus 1 or maybe worst case 2%. We've seen that OLED, microLED, and other emissive displays present increasingly challenging measurement scenarios. They have high resolutions relative to the resolution of image-based measurement systems. They have inherent pixel-to-pixel luminance variability, making display correction a necessary quality control measure. Traditional pixel registration and measurement methods were developed for large format LED display measurements. These measurements took hours because they were measured in sections, so that the sensor pixel ratios were very high compared to the display pixels. When used for correcting OLED cell phone displays in a single measurement, these methods are inadequate. They can introduce significant error in the final measurement, which manifests itself as strong pixel-to-pixel variation in the final DEMURA process and negates the benefits of correction. Alternatively, the new fractional pixel method enables a single imaging measurement of the entire OLED display to achieve very accurate results. In fact, as we've shown, a fractional pixel method is proven to enable these measurement systems to match the accuracy of microscope measurements used to capture small portions of the display. This method then ensures the effectiveness of the DEMURA correction processes for consistently high-quality display appearance. With that, I'd like to thank you for your attention. If you have any questions about this presentation or Radiant's display measurement methods, please visit us at radiantvisionsystems.com.